So we are listing problems you hate. And so far, number 1 on the hit parade is force of tension with 2 cables.
Can we go over a slant one just for extra practice?
Yeah, slant surface acceleration problems. What else? Okay, so net force multiple vectors. All right, what else? Is that a net force multiple vectors? Because I can't remember what the numbers are. Yes. Which is a net force multiple vectors. Okay. Are there any other categories we're missing? I mean, really, these are, because you guys can all do simple straight up and down force of tensions. So force of tension with 2 cables, slant surface where we have acceleration, and those pesky, remember how I said the non-perpendicular vectors in motion were going to come back? That's all that those net force multiple vector problems are. So, yes?
Can we do one with the 2 cables where they have like different angles?
We can, but I'm going to put that at the bottom of the list because I'm going to tell you in all honesty, I'm never going to give you one of those on a test. We can totally do one.
I was just like, because I know
but I am
a lot of them are the same, but there was like one on like a worksheet or something where it's like different.
No. The only one with 2 angles on a cable that you have is the hanging dog. And that's just a beast, and it's one of those things where I want you to have had that experience. I'm never going to ask you to lift that much again. I want you to have seen how it was done, but we're not going back there. Do we want to just scratch that off? Good. Okay, so we're now going to pause this. We're going to break Alexis's stuff, and then we're going to come back. Thanks. Okay, so we got a 23 kilogram object hung on 2 cables. Let's say these cables make a 38-degree angle with the ceiling, and we want to know the force of tension in each cable. Okay, so it always starts with the free body diagram. We know that this is the force of gravity, which is equal to mass times gravity. And I was gonna mention, and I think I get kind of sloppy in some of my videos. Make sure that your subscripts look like subscripts and they don't look like another variable. Not because I'm going to mark it wrong, but because it's an easy way to confuse yourself. And I've done it to myself. Like, where did that extra variable come from? Oh, it's not. It's supposed to be a subscript, but I made it too big. So F sub g equals mg, and we're interested in ft. And, of course, we have ft1 and ft2. So we could do the sum of forces on the x, but that really just proves to us that the forces of tension are equal. We're going to skip that for now because I think you all know how to do that. Well, why do we solve this on the y-axis? Because the y-axis is where we have, this is like one of those logic puzzles. Susie likes carrots and lives in the house next to the person whose favorite vegetable is green. The person in the blue house likes, have you done these kind of logic puzzles where you're filling in? That's kind of like what these are. And so you have on the y-axis a known piece that you can relate other things back to. So that's why we solve these on the y. So let's do our sum of forces on the y. Sum of forces on the y is equal to, oh, and this is also accelerating upward at, that's what we needed, accelerating up at 7.0 meters per second squared, which is a pretty good clip, actually. That would be terrifying. So sum of forces on the y, well, what's it equal to? A couple of things. Number one, we can split these forces of tension into x and y components. And our y component is opposite that angle, 7.0 meters per second, sorry. So sum of forces on the y, well, it's all the forces up minus all the forces down. And we have 2 forces that are up. we have force of tension Y1 and force of tension Y2. We only have one force down, and that's the force of gravity. That alone is not enough to solve this. We have to know what those numbers add to. So if it was just hanging there, they'd add to 0, and this is all really easy. But in this case, it's actually accelerating upwards. So the sum of forces on the y also equals the mass of the object times the object's acceleration. Well, now we got something we can sink our teeth into, because now we have the ability to set this equal to that. So mass times acceleration equals force of tension y1 plus force of tension y2 minus the force of gravity. So the pieces where you can screw up here. Forgetting that you need to create that expression for force of tension y. That would be one way to screw up, and I've seen people do that. So force of tension y is equal to the force of tension times the sine of theta, because it's opposite our 38 degrees. And, you know, we've got force of tension 1, force of tension 2, so force of tension 2 times sine theta 2. Now, we were told that theta 1 and 2 are equal. We know that force of tension 1 and 2 are equal. So we don't really have to do that. We can, two ways to handle it. You can say that that's 2 ft sine theta. Somebody, I forget who, liked to factor out the ft and have ft times quantity sine plus sine theta plus sine theta. Either one is acceptable. Either one is algebraically correct. So I'm going to go with my usual is 2 ft sine theta minus fg. So now it's just rearrangement. So mass times acceleration. I'm going to move force of gravity over. That's equal to 2 ft sine theta. Well, I know that force of gravity is just mass times gravity, 2 ft sine theta. And I could do some fancy stuff. I could factor out an m there. There are problems in section D where we're going to rely on doing that a lot. But right now you don't have to, so you can just do ma plus mg. It doesn't matter at this point. Are you pretty confident from here that you can solve this fluidly? Is it getting to this step? I mean, you know, so from here, you're, of course, just dividing by 2 sine theta, and that gets you ft. Okay? Good? Okay, so we did slant surface, or we did force tension 2 cables. Let's do some slant surface acceleration, or let's do at least one slant surface acceleration. Most often when we're looking at these kind of problems, we're looking for acceleration. We could do some other ones where we're looking for mass or looking for something else, but we'll just, for right now, we'll go ahead and do the 15 kilogram box. So we want to know if the force up, let's see, let's go ahead and we'll make this an applied force. Ooh, I got a good kind of problem. I got a good one. I forgot about these. If the applied force on this thing, and I don't know the answer to it, so those are my favorite kind of problems. If the applied force is 325 newtons, is this thing accelerating up the slope or down the slope? Where is it accelerating? Is it accelerating? Is it staying still? We don't know. So it's a 15 kilogram box. We have an applied force upslope of 325 newtons. Let's put in all our other forces. So I've got force of gravity, which I'm going to divide into force of gravity on the y, force of gravity on the x. I've got normal force. That's it. Do I have any other? Am I missing anything? I don't think so. So what we want to know is what's the acceleration of the box? And this kind of problem is trickier, and I will give you more of these, I promise. This is trickier because I don't tell you if you're looking for an acceleration up or down the slope, so you have to be really careful about your signs. Your signs are going to tell you if this thing is accelerating up or down. Basically what you're asking is that 325 newtons enough force to overcome gravity and pull this thing up the slope? That's the question. So let's kind of shrink all this. And I've drawn this in such a way that my upslope value is going to be positive if I think Cartesian, and that my downslope value, which is gravity, is going to be negative, which we're all intellectually more comfortable with gravity being negative because that's how it works in our lives. So I'm going to do I need to do sum of forces on the y? I mean, here's what I'm going to do, just more for habit than anything else. Is this thing spontaneously rising into the air or sinking through the surface? Nope. We weren't told it was, so we're going to assume that it's not levitating. They usually mention that kind of thing. So sum of forces on the y should be equal to 0. That's going to be equal to normal force minus force of gravity on the y. And we're just going to leave that there. So we've kind of proved that we've got that. We could figure out the normal force if we wanted because we know the mass of the object. Now, sum of forces on the x, because that's where the action is. And this is one where we've tilted the x-axis so that we have to only resolve one force, not two. We know that that angle in there is going to be our 29. And force of gravity on the x is opposite our 29, just as a side note. So I might do this for myself, right? Force of gravity on the x equals force of gravity sine theta. And that's just a reminder for me. So all the forces, and here, you know, we can say right, left, whatever. All the forces right minus all the forces left. We only have one force being applied to the right. Sum of forces x also, therefore, is the applied force minus force of gravity on the x. And though we don't know if there is even any acceleration, we know that whatever the acceleration is, it's going to be on the x-axis, and whatever it is, the sum of forces on the x will be equal to it. So now we'll do ma equals force applied minus force of gravity on the x. So acceleration is equal to the applied force minus force of gravity on the x. I subbed in Fg sine theta, all divided by the mass. Somebody get me an answer. I want to know if this thing's moving. Okay, so I'm not even going to finish this. You guys finish it. I trust your answers. You plugged in numbers. You get 16.91 newtons. So since it's positive and we treated this as a positive, that is upslope. So, what? Oh, duh, yeah, it's meters per second squared. Dimensional analysis, or just paying attention to your units. This thing's actually cranking up the slope. 325 newtons is fine in terms of force needed to move this thing up the slope. We are overcoming gravity in spades. When we get into friction, you will get problems where you have objects on slopes and you have a coefficient of friction, and you have to decide if the object is moving up the slope or sliding down the slope or staying still. So this is just kind of a preview. Oh, they're fun. You'll be fine. Okay, does that help with the slope? Okay. All right, so let's do a net force multiple vectors, and we'll have time to start one, but we won't have time to finish it, I can guarantee. So let's say we have an object here. We'll make this a north-south-west kind of thing. So we have a force of 10.0 newtons due north. We have something at, we'll say that's 20.0 degrees south of east. This is force 2, and we'll make that 15 newtons. So we have F1, F2. Let's get all crazy here and do something at... That's supposed to be 10 degrees. It doesn't look much like it. 10 degrees west of south, and we'll make that also a 17 Newton force, so force 3. All right. First thing we have to do, first thing I do for myself anyway, let me move that over here, is I visually remind myself that I have vectors there. That I've got component vectors for those two. Because, and I usually do this also, F2 on the X, F2 on the Y, F3 on the Y, F3 on the X. And it helps, I find, if I write a little expression that reminds me what these are. So I know that F3 on the X is going to equal F3, and it's opposite, so sine theta and F3Y is going to equal F3 cosine theta. I know that F2 on the X will equal F2 cosine theta. F2 on the Y will equal F2 sine theta. Doing that little bit of setup seems like a nitpicky accounting type detail, but it helps because then when you go to actually do the math, you have all those details listed, and you don't have to do that piece. So, for Pete's sakes, there. Okay. I'm going to do sum of forces. I know that my resultant force, I should say this right off the bat. My resultant force is going to equal the square root of the sum of forces on the X squared plus the sum of forces on the Y squared. I know that. So now I know I have to find sum of forces on the X, sum of forces on the Y. Well, let me shrink. Okay, I'll finish this and post it. Okay, so based on that, that tells me immediately that I need to find my sum of forces on the X, and I need to find my sum of forces on the Y, or my net force on the X, my net force on the Y. Don't care what you call it, you know what you got to find. So I'm going to make a quick list of all the forces that exist on the X axis. Well, I see that I have force 2 on the X, force 2 on the X, and I'm going to make a little note to myself that it goes that direction. That helps me. And that's in opposition, so I'm going to subtract these to force 3 on the X. And I'm going to, again, make my little note there that helps me out. I'm going to do the same thing for my forces on the Y. Now, on my Y-axis, it's a little bit more complicated. I have force 1, which is up, minus force 2 on the Y, which is down, minus force 3 on the Y, which is down. Now, since I already did those, to me this simplifies things a little bit, because I can just go ahead and plug those values in. Sum of forces on the X is equal to, well, let's see, F2 cosine theta minus F3 sine theta. I can put in real values for those. I didn't write my plugins just to save space and time. That gets me 14 and change and 2.95, etc. So when I subtract that out, I get a net force. I get a magnitude of 11.14, etc. And notice that it's in this direction, and I can tell that because this value is in this direction, this value is larger, so I know it's going to be thus. I also, because I essentially made this one negative, know that because the net force on the x is positive, it's heading in that direction. That's going to help me in a minute. Okay, so to get into specifics on these, for the force 1, it's easy because it's all on the y-axis. There is no force 1 on the x-axis. For force 2, the the y-axis component is F2 sine theta, and for F3, the y-axis component is F3 cosine theta. So when I put real numbers in there, oh, and note, I did draw my little arrows here over these, though I've also made them negatives, and that helps in the end when I'm looking at magnitude and direction. So let's get some numbers. So I did go ahead and just plug them all in one go. And what I get for my overall magnitude is negative 11.8720 blah, 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 newtons. So that's down, and that means that the value of these two numbers was greater than 10 newtons, which we probably could have expected. So how does this help me get my resultant? Well, remember that these little arrows are what you need. So I'm actually, and these are pretty easy because they're close in magnitude. So I'm going to draw, this is my sum of forces on the x, and the magnitude's 11.1, etc. Here's my sum of forces on the y, and my resultant, of course, is going to be the hypotenuse of that triangle. So it's pretty darn close to a 45-45. It's not perfect. But when I get, so I draw that, and I drew that again using these little arrows, these little notes that I made to myself, because I sort of pulled that all out of the original free body diagram to get that information. So let me put some numbers in. Okay, so I didn't show all the gory bits, but when I take this equation and do the square root of sum of x squared and sum of y squared, what I get for my resultant or net force, F net, would be 16, I'll just go straight down to 3 sig fig, 16.3 newtons. Now the problem a lot of people seem to be having is with the heading. So remember, I'm looking for an angle here, and it's easy to find the angle inside your triangle, and you could find the flip side of this triangle. But if you look at this, I now know that it's inverse tangent of sum of forces on the y over sum of forces on the x. And that should get you theta. All right, that's it. Have fun.